When the switch is open, these capacitors are in parallel, and we can replace them with an equivalent capacitor. Now these capacitors are in series, and we can replace them with an equivalent capacitor. Now we can say that the charge on this equivalent capacitor will be equal to this term. Now, when the switch is closed, then both these capacitors are shorted. Note that it may appear that only this capacitor is shorted. But since both the capacitors are between the same set of points, so this capacitor is also shorted. So we can remove both of them from the circuit. In this case, charge on this capacitor is equal to this term. So there is an extra charge in this system equal to this term, which must be supplied by the battery. Now, to find the charge passing through the switch, let us consider the initial charge on each capacitor. We already know the initial charge on this capacitor. Now considering this equivalent circuit, we can say that ratio of potential difference across these capacitors will be equal to this term. And potential difference between these points will be equal to this term. Therefore, charge on these capacitors will be as shown. Note that as this system is in series with this capacitor, so we could directly say that the total charge on these capacitors will be equal to this term. And as these capacitors are equal, so this charge will be distributed equally on them. This gives us the same result. Now, when the switch is closed, these capacitors are discharged. That is, charge on this plate moves to this plate, passing through the switch. And charge on this plate moves to this plate, passing through the switch. Also, an additional charge flows from the battery, which is equal to this term, and this also passes through the switch. So the total charge flowing through the switch is equal to this term.